So in this problem, we have long and straight rod charged with a charge Q, positive charge, and the rod is length H. It's a thin rod. So we can neglect the thickness of the rod. And we need to find the potential, electric potential, and electric field of this rod. And the problem is limited that our field vector is much smaller than the length of the rod. It's very small. So this problem can be solved using Coulomb integral for the potential, and then electric field can be found as a gradient of potential in negative direction. So first of all, let's define source and field points. So if we assume that the rod is thin, our field point would be on the rod. Our source point is on the rod, and the field point is pointing somewhere nearby. And then we can write for the field point that it's equal to, in cylindrical coordinates, so they don't have the same z coordinate. We have z prime for the source vector, source point vector, we have a prime. However, the direction of unit vector, z prime, is pointing in the same direction as z vector. They are equal, and then the prime can be removed. Now the r vector is this part. So field point vector minus source point vector. That unit vector can be taken out of brackets. And the absolute value of this vector is this part, taken a square of and then a square root of. So it will be r squared, and then r unit vector times r unit vector is 1. It's r squared plus this 2 multiplied times 2. However, we have a 2 scalar product of 2 unit vector r and z is 0. And then this part again, z times z is 1, and this part is squared. So now we can plug it in the Coulomb integral. So in this case, the dl is the length of the rod. So it can be replaced with z prime. And dz prime is related to this distance. So z prime minus z, where z is very small, something very small. And then we can introduce a new variable equal to z prime minus z. So the larger minus something small. And we can plug it in here because here is a square, so it doesn't matter actually. So they're switched. And then the limits of integration along z prime. If we put the origin in the middle, that we have h half below minus h divided by 2 and h divided by 2 for the positive axis. And then we have introduced this value. So the limits of integration would be that h divided by 2. And we can rewrite so using the new introduced variable will help us in integration. And there is a formula to solve such shape integrals. So then using this formula, we can simplify the integral and find the solution. Okay, that's what I have for the limits of integration. Let's plug it in. And then we also know that we will have a natural logarithm with this minus another natural logarithm with this. So we can already write one natural logarithm and divide one on another. Limited space here. Hope you can see it on the video. So that's what I got. Let me check if it's correct. So it seems to be fine. And now we would need to simplify this natural logarithm to find the solution. Because we know that h is big, but r is very small, and z is very small. So let's see what can we do. So we can write the natural logarithm again for the further simplification. Since the numerator and denominator are almost identical, so I have one expression which is for both numerator and denominator. And I want to simplify it. So to do this, we think about what is the large here is h, and then we can take it out of the bracket. Okay, that's what I have for the expression, natural logarithm. And we know that since h is big, we know that z divided by h is small. This one is also small, and this one is also small, due to our conditions in the problem. So let's remember this equation. Let's mark it. And now we assume that this, and this are very small. So let's try. Right? Sorry. H is here. So then we have two different answers for numerator and the denominator. So in one case, the answer would be h, and in another case, the answer would be 0. So the h would be for the case where there is a plus. So it's upper part of this division. So it's numerator. For numerator. And 0 would be then solution for the denominator, which we obviously cannot use. Cannot use it, so let's expand. Let's use a Taylor expansion to find the solution for the denominator. So the Taylor expansion I will use here will be as follows. One plus epsilon root of so that's the Taylor series I will use. And so using this Taylor series, we can simplify the expression for the denominator. So going back to this expression, now we're interested only in the denominator, so minus Okay, so this is expression for the numerator. We can open this bracket to have it uniform under the square sign to bring it closer to simplify this Taylor series. Okay, that's it. Now we can bring this 4 out of the square root sign. I swap this 2 in place. Mistake here. Yes. Okay, that's it. Right? Oh. Right, if we put this back, we will come to this expression. Yes, yes, this is correct. So now we have the expression to apply the Taylor expansion, Taylor series. So it's 1 plus epsilon in a square root. Here is also a square root. Keep it consistent. And now we can use the expansion. The first is 1, then plus half times epsilon. And then minus 1/8 times epsilon squared. So we bring it till the cubic. So everything above the cube we can sum up together as two small numbers. So then here will be left only this one, right? So the squared, so 16. And the rest we write in this small function. So let's see what we have. Let's simplify it. So here we have a half. Here we have 1 divided by 4. And then let's plug it in this to open the brackets. And the last part, we still remember about this half. And then times, will be 16, 1 divided by 16, so this also cancel each other, but we can minus z square, and plus everything else. So, this and this can cancel, this and this. Great. The answer for the numerator is r squared divided by h. This h times the rest. So now we have two answers for the numerator and denominator. The h was here found quicker for the numerator. So let me write again the solution of the Coulomb integral. So I think it was something and then we had that natural logarithm with a really large expressions. So we now got h for the numerator and was it was r squared divided for h for the denominator, so it's gonna flip. And we have here r squared. So to simplify further, so this squares can be taken out as a number 2. Okay, that's the solution for the potential, electric potential. And what one can notice here, what if the H and R is equal, then if H and R is equal, then the potential becomes 0. Because the natural logarithm of 1 is a 0. So the second part of the question, the electric field. Electric field can be found grad phi. And what do we have here is cylindrical coordinates. So we can write then the gradient of potential in cylindrical coordinates. So it's implying we are in R direction. We have minus from here. Minus 1 divided by R. This is by R, now it's by phi. d phi potential by d phi angle in phi direction and minus d phi by dz in that direction, right? Okay, so looking back to our potential, we need to take these derivatives. We have only r, we don't have z, we don't have any phi, so this part becomes 0 because of this derivative, and this part becomes 0. Left. This is, so we have left minus minus and then 1 divided by r. So that's what, in the r direction, of course. That's what I got. 2 pi. Why did I got 4 pi? Yes, of course. This is 2 pi. 2 pi epsilon naught. Yes, this is a solution for the electric field of this long thin rod in r direction and it looks like a Gauss law.